This is day 2 of our workshop. I think most of you were here yesterday. This is what today's going to look like. I'm going to start off with kind of an overview of how the prover works a little bit, and then we'll jump back into working on rules and whatnot. So you can see here kind of what today's going to look like. Yeah. So the talk I'm going to give was written by my colleague Chandra. Kind of goes into the nuts and bolts of how the prover actually works. So let's take a look. So far, you've had kind of this sort of view of the prover. You've had your kind of your code, your Solidity files, your spec files, and we've kind of mushed them together and sent them off to this black box. And you get either a green check mark or a counterexample, and you guys have kind of had that sort of view. So what sort of happens in the middle here? Well, a very, very high level view of what happens is we take the code, we take the spec, and we sort of combine them together into a logical formula. Now this is a very simple view of a lot of complicated steps. But once we get this logical formula, an SMT formula, we send it off to a bunch of off-the-shelf solvers. So if you've heard of Z3, CVC4, 5, yikes, a bunch of tools that are able to handle these mathematical formulas with a bunch of theories and whatnot. And then those tell us whether or not they found a bug or proven the spec correct. And then we do a back translation to get the result that you see. So kind of the high level steps here. We take the Solidity file, compile it, and break it down to a bunch of simple operations. So that's partially done by the Solidity compiler, and then we have some other simplifications that we do. We also do some optimizations, and all of these simplifications and optimizations, we're very careful to make sure they preserve the meaning of the program, because obviously if they didn't, we would be proving nonsense. And then once we have the programs, usually on the method level, broken down and simplified, we then wrap that with our specification, which you've seen CVL. That's our ergonomic DSL, as we say. So zooming in a little bit more, this is kind of the overlying architecture that we're going to go through step by step here. So you can see the compiler, decompiler, static analyzer are kind of those simplification steps. VC generator, that's turning those instructions into a formula. And then, like I said, we send those to some constraint solvers, some SMT solvers to do the kind of final hard work for us. So throughout this talk, we're going to look at a motivating example here. Pretty simple, probably much simpler than what you saw yesterday. But it'll kind of show us the basic points. We have some state that can get modified. So we have funds mapping, and we have a couple methods. One that changes the state, and one that views the state. So deposit, get funds. So one question we might want to ask is, how do we know for sure that deposit increases funds by amount? Now you could spend a lot of time just looking at this and convincing yourself. That's oftentimes what we do. But we'd like kind of a stronger guarantee here to catch those little cases that we might not think of, especially when it comes to what exactly are the semantics that the Solidity compiler is generating for us. And I think between 0.7 and 0.8, this actually did change math, like the semantics of math. The default semantics changed, which is kind of weird. So we kind of reason a bit deeper than the surface level here. So let's jump into the first step, the compiler. So we shell out to the Solidity compiler. That's pretty simple. It gives us bytecode. In theory, we can support other EVM languages because our tool is specifically working on the bytecode and not the source code, which is why we compile the source code first. Which means in theory, we could get a contract just as bytecode. In practice, there's a bunch of things we grab from the source to help us along. But in the degenerate case, we could definitely support pure bytecode. And what's really cool about this is a lot of the analyses that we have to write reason about generated code. And we're thinking about, okay, what memory properties, storage properties does the compiler give us? And can we prove them in our analyses? And that's led us to finding quite a few bugs here and there within the EVM code generation part of the Solidity compiler, specifically with storage and memory, because we've been trying to prove some properties that are helpful down the pipeline. Yeah. So then once we've ingested the bytecode generated by the Solidity compiler, we then translate it to our own intermediate representation, what we call TAC, which originally meant 3-address code. We kind of break from the 3-address convention a couple of times, but the name has stuck. So basically, this gives us a couple things. We turn, I don't know how familiar you are with the EVM, but that runs as a stack machine with a max height of 1024. With a max height, it means we can break that down into a register machine. So we don't have to reason about offsets in the stack. So we turn all the stack slots into registers, which makes things a lot easier, reasoning about where data flows much easier. So that's one major thing we do. There are also a couple little instruction simplifications so that we don't have as many cases to reason about. But again, this is all meaning or semantics preserving. And like I said, this makes it easier to analyze. To give you an idea what this might look like, I have an example here. Our bank contract will generate like a big, long file with lots of little instructions. So like this small code turns into pretty similar to what you'd see in regular code generation. Big, long file with a lot of instructions. So let's move on to the next step. So after we've translated into our intermediate representation, then we want to do a lot of things to make the job of the solver easier. So what's really cool about solvers is they're big, general purpose. They can reason about a lot of things. They're really clever. They're really smart. But because they're general purpose, there are a lot of cases where they may not work as well for us. So we can do a lot of more special analyses specific to our code that makes the job way easier for the solvers. So we do a bunch of static analyses, a bunch of classic ones. We gather some points to relations. One thing, this third point, we segment memory into disjoint non-interfering sets of pointers. So basically that means if you access one piece of memory, if we could say, well, hey, there's this one region over here that we might modify it and maybe we're not sure exactly where, but then there's this other region over here. Then every modification to region A, we don't have to even think about region B. So that means that there's a smaller set of modifications that then the solver has to think about. So these are kind of the things we're trying to do. We're trying to give just easier queries to the solver, and it turns out a lot of these classic analyses can help a lot, and many of them kind of build on each other. Right. So, for example, if any of you are not familiar with kind of what static analyses might look like. Here's a very tiny example. If you look at this baby program down on the right, we have a couple of structs in memory. We modify one field of one of the structs, and then we assert something about a field of a different struct. So one thing we could say, since we're only worried about this assert statement at the end, we're only worried that assert x.f equals 1. Because our analysis can tell us, oh, the assignment to y.f equals 3 does not affect x, then we can actually remove those instructions from the program, and it will not affect the semantics of the resulting formula. It won't affect our assertion. So we can get rid of that, and then the solver doesn't have to think about what's going on there. Because eventually it would realize that the value doesn't matter, but that's a bit extra work for it to do. So this is a huge part of our pipeline. It does a lot of the heavy lifting, especially when it comes to thinking about memory and storage, argument passing. There's a lot of stuff that it has really helped streamlined. Right. And then the next part of the pipeline, once we get all these optimizations in, then it's time to encode this program-ish into a mathematical formula. So VC stands for verification conditions. This is a type of encoding of a program. What are the conditions under which we verify this program, more or less? So you may or may not have gone into Hoare triples in the past, but we're going to take a look here. So a basic Hoare triple, and this is kind of what you're writing in the spec, right? And we'll kind of look at why that looks that way in a sec. But so a basic Hoare triple looks, it's usually written like this: P in some brackets, a statement S, and then a postcondition Q. So what we can say, or what we would like to say about a Hoare triple, is that if P holds before executing the program S, then the predicate Q holds after executing the program S. And then we have this thing called weakest precondition. And the weakest precondition kind of helps us reason about the precondition we might write. So the weakest precondition of a program S and a postcondition Q is I'll just read this out here, is the weakest predicate such that Q holds after executing S. So this is kind of a way, if you have S and Q, this is a way to compute some sort of the weakest precondition. And we'll see why that's important. To prove a triple PSQ, you can just imply that P implies the weakest precondition of those. I understand this is a lot of lingo here. So basically, there's a standard way to calculate this weakest precondition, given a program and a postcondition. So you can apply a bunch of kind of rote syntactic rules, kind of moving backwards through the program to convert the program into a big long predicate. And then you take that big formula, you take your P that you wrote, you construct P implies weakest precondition, and then that's what we send to the solver, more or less. And that's kind of what this last formula is kind of what I just explained. If we can show that P implies the weakest precondition, then the Hoare triple holds. Hopefully that makes sense. There's a lot of stuff going on there. Feel free to ask me after, or if anyone has questions now, feel free to let me know. Otherwise, I'll move on. So where do P and Q actually come from? I kind of hinted at this earlier, but they come from the spec. So our rules are kind of Hoare triples, basically. So let's go back to our example. How do we know that the deposit function increases funds by amount? So first we need to somehow write that down in our rule in a formal way. So you guys have probably seen more complicated rules than this by now. But we have a symbolic amount. So this means amount can be anything. We have some environment, also could have any message sender, any whatever. And we say something about the funds before. So we're saying before deposit equals whatever the funds are at that point. Now we could, so that's essentially what we're doing. The precondition is that before deposit has whatever this value is in the contract state. That's our precondition. Then deposit would be our S. So this was our P. Deposit, all the code that gets inlined, we just inline the entire function there with the symbolic value amount and symbolic environment E. So that's our S. We gather some more information, and then our assertion is our Q, is our post condition. So those are our pre-post and the program. And then this is exactly what gets kind of pushed through the pipeline, and eventually you get those that encoding of the weakest precondition. And as we probably talked about before, this must, since the values are symbolic, they're covering every single value of amount. Let's see here. So we've gone through the whole pipeline. We've turned the program into this formula and encoded our query in the form of P implies weakest precondition. And then we send it off to like 4 different solvers or more in parallel, and kind of see what do they think. And sometimes one is a bit faster on one thing than the other. They all got kind of different strengths. So that's kind of why we just send it off to all of them. And in this specific example, which I hinted at earlier, there's some overflow because I believe we did this back in the older version of Solidity when safe math wasn't automatically implemented with those operators, which is kind of, this is a pretty simple naive bug, but it kind of shows how the prover can find those weird edge cases that you might not think of. So just as kind of an overview, again, the pipeline has a few steps. We take the Solidity file, we get the EVM bytecode out of it, we turn it into our own language, we do a bunch of clever optimizations around it, use this classic verification condition generation, and send it off to the solvers that we have to then tell us kind of what they think, whether they can prove the program correct or they can find a counterexample. So that brings me to the end of this talk. Do we have any questions? Is there anything you'd like me to go back to, or did that all make sense? Clear as mud. Yeah. Yeah, yes. So the question is, when we get the counterexamples, what sort of back translation do we have to do? Yeah. So when I started, which is not how things work now, when I started, that was a very weak part of our tool. A lot of times the variable names in the SMT formula were just the same, and we just kind of had a local variables block, and there was no real translation other than these are the ones we have. But now as we build our, as we do the optimizations, as we kind of plumb the program through our pipeline, we build on some optimizations. We build on some annotations that tell us, that keep hold of the translation information back to the original program. So then by the end, we still have these annotations around saying, oh, well, the variable that we generated, x125 in the formula actually translates to this variable at this point in the program. And so it was and still is kind of tricky. We don't handle all of the cases, especially when it comes to storage and memory. But that's something that's definitely getting better. But is not easy. Wasn't easy, and kind of came later as we realized, oh, we'd actually like to understand the counterexample better. But you're right, very very tricky sort of part of the thing.
You also need to have those annotations in the bytecode, so do you fiddle with the compiler?
Right. So we do not. Sorry. Yes. I am mostly referring to local variables in our spec. So our spec has, for example, you have amount here, parameter to the rule, env. So those sorts of variables we have the names and information for. We do not have the local variable information for functions. I believe we are starting to get some storage, like global state variable information, because we know exactly where to look in storage because we ingest the storage layout from the compiler. So that allows us to get those high level names. I'm not sure exactly the state of that, but that's something that's more doable than the local variables. Yeah, thanks for clarifying. Any other questions? All right, sweet. Cool.